Okay, we can start. Thank you. All right, good afternoon. Okay, let's start by quickly reviewing what we did in the last lecture. We talked about, in fact, I think we talked about MOS IV characteristics. I consider that a review. A few things I'll mention. One is if you are not familiar with thinking about MOS transistor using an energy band diagram extending from source to drain, as I draw here, I recommend that you take another look at that. This is the energy band diagram drawn from the source across the channel region into the drain. For the case VG less than VT, such as when VG is equal to VFB, flat band voltage. When VG is less than VT, there's a large barrier between the source and channel. That is why current cannot flow between source and the drain. Now, on the other hand, the bottom diagram is drawn for VG, let's just call that equal to VT for now, or larger than, I suppose. VD happen to be larger than VS, all right? The important thing is to note that when VG is equal to VT, the barrier between the source and the channel is reduced sufficiently for a large density of electron to appear in the channel. Right? That's a way to understand the inversion in terms of this energy band diagram. And when there's a free flow of electron between the channel and the source, any additional voltage between source and drain, a presence of voltage between source and drain, will cause the electron to flow from the source to the drain, and that gives us the IDS, the drain to source current. Okay. And again, if I can ask Kevin to change this, I want to show a little bit of field here. All right. Just indicate this current flow. That's the subject of last lectures, talking about current flow here. All right. Now, we actually talked about a few other things. Let me briefly mention this. I think we introduced this relationship between VT and the body bias, VSB. VT is the linear function of the body bias, VSB. All right? That's a little different from perhaps what you remembered as the body effect. Mathematically, you might remember there's a long square root term. But I think this is just as good a model, maybe even a better model today. And this body effect or backgate effect also has an impact on VD set. It makes VD set equal to VG minus VT divided by 1 plus alpha, or we call it M. M is 1 plus alpha. Yeah? And has an impact on ID set. Makes ID set equal to, well, maybe we can do this together. There's the W, of course, over L. There's the mu times Cox. Actually, there's over 2 here also. All right? And you probably remember the remaining term is VG minus VT squared. But we have shown that there's a over M factor added as a result of the backgate effect, or more commonly known as the bulk charge effect. Okay. We also talked about why the current saturates beyond VD set, and in the discussion session we had some discussion of the random telegraphic noise, and from that build a picture for interface traps and the 1 over F noise. Any questions about that? Okay. If not, let's move on. We go to a section called charge sheet IV model. Now you have seen this term charge sheet before. That's in the previous section. We're talking about relationship between phi S and VG, or between inversion layer charge and the VG. Now we're going to use a similar model to derive an equation, IV equation. All right. To introduce that, let me point out that if we draw the ID versus VG, not only we have a region where ID increases linearly or proportional to the second power of Vg minus Vt, which is this part, strong inversion. There's also some current flow at Vg less than Vt. Now you all know that's called the substratal current, right? So due to the weak inversion of the channel, there's some current flow even when Vg is less than Vt. And that current is more clearly seen in a plot of logarithmic ID versus Vg. If we plot log ID versus Vg, then this is what we see. That is, there is a region where ID is proportional to Vg minus Vt, shown here, when Vg is larger than Vt. When Vg is smaller than Vt, current varies with Vg in an exponential manner, so it's a straight line. And specifically, we have seen in chapter 3 that Q inversion is proportional to exponential QVG over NKT. N is always larger than 1, if I may remind you. N is actually equal to 1 plus C depletion over C ox, right? And it's always larger than 1. Because Q inversion varies with VG in this manner, one probably would expect ID varies in a very similar manner. And that expectation is absolutely correct. The problem with this way of looking at the IV characteristic is that it's a piecewise model, right? We understand this part of the IV as a linear relation between VG and ID. Then we separately understand the substratal region as an exponential relationship between ID and VG, right? It's piecewise. What about in between? You know, is it possible to have an equation that gives us a continuous function of ID as function of VG? And that's what the chart sheet model will give us, okay? So we'll see how it does that. Okay, next. Now we start with this equation. ID is made of two parts. It's made of a drift current and a diffusion current. So in this review that we did last time, we only looked at the drift current. We did not consider diffusion current. And partly because of that, we could not see the, we would not have been able to derive the correct equation for the substratal current, all right? So here we carry the drift current and the diffusion current. Now the drift current, just as we saw last time, is equal to mobility times W times Q inversion times electric field. Is that right? Okay? Let's not worry about the sign. Sign does work out. So mobility times W, Q inversion times the field, right? The field here we express as d phi s dy. Now, last time we wrote down dV, or V sub C dy. V or V sub C is the channel voltage. And there's nothing wrong in thinking about that. But here we go back to a quantity that we emphasized in chapter 3, phi s, because we certainly understand what that phi s is. Phi s is potential right at the surface. Is that right? Okay, so we're going to explicitly emphasize phi s. And later we'll relate this phi s to Vg. Okay, we know how to relate those two. So that's the drift term. What about the diffusion term? W makes sense, right? Times the diffusion constant, which is kT over Q times mu. Remember the Einstein relationship, right? So diffusion constant is equal to kT over Q times mu times dQ dy. Yes? Right? The gradient of the carrier concentration. Any questions?
Yeah.
Yes?
Could you explain the difference between VC and phi s?
VC and phi s. It's very good. Phi s, the definition is fairly clear. It's defined as the band bending, defined as the potential at the surface. If we take the substrate as being the reference, yeah. Go back to chapter 3, the first few lectures. So that's phi s. Okay, it's very clearly defined. Is that right? VC we kind of pull out of the hat when we talked about the IV characteristics. Good that you asked that. VC, we kind of introduced that just by appealing to our intuition that if the channel is viewed as a resistive sheet, certainly it's possible to have potential that's varying on the sheet from the source and the drain. The main characteristics of VC is that VC is equal to 0 at source. VC is equal to VD at the drain. So once we quantify it this way, now you can ask, is VC identical to phi S? Is it? At source, is there still band bending? There's still band bending, right? So clearly phi S and VC are different. So to some extent, VC is a little easier to use. It kind of overlooks the little, maybe a little bit of a potential barrier between the source and the channel. You know, we kind of ignore this little bit of in this diagram, right? We'll call this VC equal to 0. We'll call this VC equal to VDS. Is that right? Kind of makes sense if you think about the channel as a resistive sheet. Everything makes sense. But if you really look at the detail, it's kind of a little difficult to define what VC is, right? Other than VC is connected to source, therefore should be at the same potential as source. Phi S, however, there's no ifs and buts. It's exactly this point of phi S. For example, phi S at this in the drain, in the source, would be different than phi S right at this point. You know, if it's a little different, that just means there's still a little bit of a potential difference. It will be different because why? The whole electron concentration is different in the source compared to the concentration right at the in the channel, even though it's next to the source. Is that right? So for that reason, phi S cannot be the same, given the Fermi level is continuous. And that will come out in the phi S. So phi S is a little bit more detailed view, but you know, if you first want to derive IV characteristics, if you don't have to come to the detailed view as phi S, if you can just view it as a resistive sheet, well, we'll take the second view. But here we're going to go back to that more detailed view of there's a very clearly defined potential called phi S, has to do with band bending. All right? Okay. So both are useful, and they don't contradict each other. Right? They don't happen to be identical either. These two things are not identical. All right? Okay. So ID then we'll put the mu W outside square bracket. We'll get mu W times QI d phi S dy plus KT over Q dQ dy. That's because this diffusion constant is equal to KT over Q times mu. So if we take mu out, we'll get KT over Q inside the bracket. It's okay, this next step? All right. Next, we're going to integrate the left-hand, right-hand side between source and drain. Left-hand side will integrate between source and drain, 0 to L, integrate with respect to Y. Right-hand side, we integrate with respect to phi, right? Here's the phi S. The first term we integrate with respect to phi S. Put another way, we have multiplied the dy to the left-hand side, or multiply dy to both left-hand side and right-hand side, yeah? So right-hand side becomes qi d phi S plus kt over q dqi. So let's first look at the integration of d phi S. Between source and drain, what is phi S at source? What is phi S equal to at the drain? Well, we call the phi S at sourse phi S 0. 0 meaning y equal to 0 or source. This just means the phi S at the source. Is that right? Okay? This just means the phi S at the drain. Now, do we know exactly what number, what value they hold? We don't. We have to go back to the, chapter 3 equation to relate phi with Vg. We'll do that later, right? Okay? Right now, we just call the surface potential at the source end of the channel, called that phi S0, and the drain end of the channel called phi SL. Is that right? Okay? All right. And Qi is this Qi, d phi S. Integrate that, all right? Plus the second term's KT over Q, just dQi. That's great. and integrate between Qi. That Qi, by the way, is inversion charge, right? Inversion layer charge at the source to inversion layer charge density at the drain. It's okay? All right. How do we carry out this integration? The second integration is kind of easy. It just becomes QIL minus QI0. Is that right? The first integral is difficult. We have to figure out what Qi is as function of phi. All right? What is Qi as function of phi s? All right? Well, fortunately, we've seen that in Chapter 3. When we look at the MOS capacitor theory, we already had a relationship between phi s and Qi. And here it goes. VG, or we call it VGB because now we have also source voltage and drain voltage. So when we say gate voltage is with respect to the body, all right? Not with respect to the source, right? This is how we derive this equation in Chapter 3. It's from the gate to the body. The voltages are divided between the flat band voltage, band in the substrate, and the voltage in the oxide. Voltage in the oxide is made of Q over C, and there are several Q components. There's the inversion charge Q, Qi over C ox, right? There's the depletion charge Q, Q depletion over C. It's okay? All right. Phi B, no change. Phi S, no change. Qi, we don't know what Qi is. We just say it's a function of phi S over C. Do we know Q depletion as function of phi S? Yes, we do. At least if we could assume it's uniform doping. Last time we kind of talked a little bit about how uniform doping is really not very good assumption anymore, right? Retrograde is the rule of the day, but this is just a theoretical model, kind of old model to be honest with you. So let's assume it's a uniform doping. If you want to develop this for your term project to see what you can do for retrograde doping or some more general doping profile, certainly it's an interesting project to work on. But the standard, what we see in the literature still is assume it's a uniform doping in this charge sheet model. If you assume it's uniform doping, then we know how to relate Q depletion to phi S. It's just this way, right? Gamma introduced here just to simplify the mathematics, right? You see there's the 2 epsilon s Q Na times phi s, is that right? Divided by C ox, is that right? Is okay? All right. So by substituting, and as a result of this, we move the Qi term to the left, put everything else on the right-hand side. We got Qi is equal to C ox VGB minus VFB minus phi s plus gamma square root of phi s. Did I do this right? Yeah, I did this right. So this is expression of Qi as function of phi s, which is what we needed to carry out this integral. Right? To carry out this integration, we needed Qi as function of phi s, and we got it. Qi is a function of phi s. You see here, VGB is known, right? VFB is constant, doesn't change with y, doesn't change with phi s. Is that right? All right? Phi s is phi s, square root phi s. Okay? So we're going to substitute this expression for the Qi in the integral and then carry it out integration. It's kind of easy, right? You expect to get a phi s squared term, and you expect to get a phi s to the straight half term. Is that right? And you also expect to get phi s to the first power term. Yes? Following what I'm saying? Okay. And indeed, you will get this. And maybe I should also point out, by the way, this equation is also useful to evaluate this. Once we get Qi at L and Qi at 0, we simply express them as function of phi s at 0 and phi s at L. Is okay? All right. So the right-hand side will only be a function of phi s at 0 and phi s at L, as shown in the next slide. Here you go. So after we carry out integration, we get a long expression, but it's only a function of phi s at L and phi s at 0. right? Yes? That's the first order term we expected. We also expected second order term, and there we see them. And we expected the 3/2 power term, and we see them there. Is that right? Yes? Where did this square root term come from? Any idea? Well, it came from this qi term, right? Qi is a function of square root term of the phi s. Is that right? Okay. So this is just the mathematical integration, no new physics. All right. That's the really interesting thing about this model is that it mathematically look very complicated, but really there's no new physics introduced. In fact, to me, this is always a little bit of a problem. That is, I actually have difficulty understand what this equation is telling me. Well, we'll get to it at the end. So this first half of the equation has to do with the diffusion current. Second half of the equation has to do with, the first half of the equation corresponds to the drift current, and second half of the equation corresponds to the diffusion current. All right, in case you want to ignore one or the other, it's good to keep track of which terms come from the drift equation, which terms come from the diffusion mechanism. All right? Okay. Gee, that's almost the end, but not quite. Because when we say IV model, that means we want ID as function of what? We want ID as function of things like what? VG, VD, VS, VB, right? Right now we have it as function of phi s at source and phi s at the drain. So what we're missing is to figure out what is the phi s as the source and phi s as the drain as function of VG, VD, and VS. Is that right? Okay. Actually, we have done this. We did this in chapter 3. When we look at MOS capacitor, we talk about something called the chart sheet model. Remember, we found a relationship between phi s and VG. Is that right? Except it has to be solved iteratively. You may not remember it, but we have always said we have a relationship between phi s and VG. Remember, if we knew VG, we know phi s. That's how we can translate the capacitance versus phi s to capacitance versus VG curve, right? We have always known that. It's just that relationship's complicated, right? Okay. Let me remind you, what we had in chapter 3 is actually this equation. Slightly, with one additional term, we got this new equation. Let me remind you, in chapter 3, we derived this equation. When we derived this equation, we already limited ourselves to weak inversion and strong inversion. We have ignored the whole terms. We ignored the accumulation region. When we did that, we end up with this relationship between VG and phi s. And it's significantly simpler than the full relationship, but still transcendental, still requires iterative numerical analysis in order to find the phi for given VG. But we did have this equation before, all right? So you may not remember it, but you can review your notes, you will find it. So it says VGB is equal to VFB plus phi s, 0, meaning we're just looking at a source for now. Actually, this is good for any point, by the way. Any VS, phi s, any point of y in the channel, this equation is fine. But we don't need to know phi s any points other than 2 points. One is the phi s at the source, one is the phi s at the drain. Those are the only 2 phi s's that's required for us to determine the IV curve, okay? And this is the part that, as I said, I don't think I'd fully appreciate the physics. That how come all we need to know is just this 2 point that determines the current? Well, that's because the relationship between the drift diffusion, that the peculiar unique relationship between the potential profile and the Q and the V velocity, so that multiplication is constant, that relationship was already captured in the way the problem was set up. All right? So here we see the result is that we only need to know those 2 phi at the source and the drain. At the source, that phi s0 is related to G in this manner. VGB is equal to VFB plus phi s0 plus gamma Remember what gamma is? It's constant. It's a square root of a Q, NA, things like that over Cox. That's Q, right? Times square root of phi s is our unknown, plus KT over Q times exponential phi s minus 2 phi b over phi t. Phi t is KT over Q again, okay? Is phi t KT over Q? Yeah, it is KT over Q. That's right. That's right. All right. So don't worry about this term. I'll explain this term in a minute. But if you ignore this minus VSB term, I hope this review helped you remember. We have seen this before. We have derived this before. All right. So the point is that for any given VGB, if we know that, we'll be able to figure out what phi s is. Is that right? Okay. Now what's new here is a VSB. You see, in chapter 3, we had no opportunity to add a so-called embodied source voltage because we did not have source. We only have the gate, the oxide, and the body, right? So all the voltage is VGB. Now we have these additional p-n junctions. One of them is called a source, and in general we want to allow the presence of a bias between the source and the body called a VSB. When there is this bias, specifically, typically this junction is reverse bias, by the way. If it's forward bias, this equation still applies, but typically it's reverse bias. Body bias usually reverse bias. So when there's a junction nearby and one junction is reverse bias, we now have a problem. The problem is, how do we relate phi s and phi and ns? How do we relate phi s and ns? Let me first remind you our usual no-brainer relationship. That's electron concentration is equal to n naught exponential q phi s over kt. Remember how that came about, right? If there was no phi s, if the band is flat, ns is just equal to n naught. When phi s is equal to 0, ns is equal to n naught. That makes sense. Anytime phi s is finite, meaning there's band bending, then EC become closer to EF, then the ns should increase by this term exponential q phi s over kt. Remember where it came from? Makes a lot of sense, right? It all has to do with the separation between EC and EF. Okay? All right. Now what is the complication here? The complication here is now we have two EFs. We don't just have one EF, we have two EFs. Why? Because we have a p-n junction here, and p-n junction is, let's say, reverse biased. So here I drew you a picture of that p-n junction. N plus is the source, P is the body. There's reverse bias. Anytime when there's reverse bias in the p-n junction, there are two Fermi levels, remember? One is called EFN, one is called EFP. Now the question is, which of these two Fermi levels will determine the electron concentration? Is the EFP, which is pinned to the body, you see? The way we drew, the usual Fermi level we drew, now has to be called EFP, because this is the energy band diagram of the body, yeah? So if a Fermi level that's close to EV of the body, that's our EFP. It's the P side, the body side of the Fermi level. Right? Yes? So we know now EFP is here. Where is EFN? EFN, of course, somewhere lower than EFP, somewhere here. Lower by how much? Lower by QSB, of course. QVSB. Is that right? Is that right? So now we have two Fermi levels. So which of these two Fermi levels determines the NS, electron concentration? If it's EFB, if it's EFP, then the way I drew this energy band diagram should give us, decent density of electrons, maybe 10 to the 12s, 10 to the 14s, yeah? But if it's this EFN that determines the electron concentration, now EN is far away from the Fermi level. So we should have extremely small density of electrons. Is that right? So you see we have that problem. Which of the two Fermi level, cross the Fermi level, should determine the electron concentration? Now you may know the answer. If you know, then this should be easy for you. If you don't, then I'll tell you that the answer is that whenever you have a bias between an M plus region and P region, it's the Fermi level on the M plus region that determines electron concentration. Why? Because it's the M plus region that provides the electrons to the inversion layer. Right? So the electrons must be at equilibrium with electrons in the M plus region. That's where the electron come from. The electrons in the inversion layer does not have to be at equilibrium with the electrons in the body or with the holes in the body, to be frank. That's what determines the EFP, is the hole density in the body. In fact, we have heard in chapter 3 that the electron inversion layer is very weakly coupled with the holes in the body. It takes many minutes for them to reach equilibrium. That's how long thermal equilibrium is to be reached if we did not have the source, remember? It takes minutes for the inversion layer to be established, right? That just shows you how weakly the inversion charge is coupled to the holes or to the EFP. On the other hand, it's very heavily coupled to very strongly coupled to the source, because that's where the electrons come from. You follow what I'm saying? All right? So clearly, what determines the phi s is not the first equation, but the second one. It's ns equal to n naught exponential q phi s minus VSB over kt. In other words, phi s has to be larger by VSB before it reaches a large value. You know, the same phi s will give us very small ns when a VSB is present. Ns will be very small. So the band bending will have to be bigger than 2 phi b before we reach inversion. Right? That last statement may be something you have heard before, that the band bending has to be larger than 2 phi b before we reach inversion. That's exactly what we're talking about here. Anytime we have a body bias, band bending will have to be more than 2 phi b, more than 2 phi b by what? By how much? By VSB, before we have a large density of electrons, before we have inversion. All right? So for this reason, if we just change all the ns expression with this change, you will see, you can show that this term should have this additional minus VSB term. Okay? So that's where the only difference between what we are using today and what we derived in chapter 3. Okay? All right? Can you accept that? That we needed this term. All right? Okay, so this equation 4.5.2 is the equation that will give us phi s 0. You see, once we know VGB, once we know VSB, we know phi s 0. Similarly, we can determine phi s L from this relationship, VGB equal to VFB plus phi s L plus gamma phi SL plus phi t exponential phi SL minus 2 phi b minus VDB. Can you explain this VDB to you? To yourself, yeah? So now you see in a transistor we actually don't just have 2 Fermi levels, we have 3 Fermi levels. What are these 3 Fermi levels? One is the body, called the VFP, we talked about earlier. One, what we call the VSN, which is Fermi level from the source side. Now the drain side gives us a 3rd Fermi level. Can you visualize that? Because the drain to body p-n junction is reverse bias at a different value than the source to body. Is that right? So now we have 3 Fermi levels. Here I'm saying it's the drain's Fermi level that determines electron concentration in the inversion layer near the drain. Does that make sense? It all comes from the basic concept of equilibrium. What is equilibrium? Equilibrium simply means, you know, anytime electrons can communicate with another group of electrons very freely and easily, the 2 groups of electrons must share the same Fermi level. The electrons in the channel near the source share the same Fermi level with the source. The electrons near the channel near the drain should share the same Fermi level as the drain. Will not share the Fermi level with the source. Does that make sense? Right? So that's why it should be VDB here rather than VSB here. okay? That all comes just from the concept, what is equilibrium, right? And therefore, what is Fermi level? Equilibrium simply tells us that certain electrons can communicate easily. That's called equilibrium. And when they are at the equilibrium, they share the same Fermi level. All right? And that's why it's the Fermi level of the drain that determines the electron concentration in the channel near the drain. That's why this term has this additional VDB, because this term describes or came from the electron concentration near the drain. All right, yes, question?
Well, what about the Fermi level all along the channel?
No problem. You can use that concept as well. The problem is, however, we don't know the Fermi level, quasi-Fermi level near the source and drain. You see, last time we already made this point that if we really insist on drawing the energy quasi-Fermi level all the way from source to drain, we can. We can. In fact, we have to find out the quasi-Fermi level at every point along Y using the relationship between N and this quasi-Fermi level. That's how we do it. So it's not very useful. Yeah? When it's not useful, we don't think about it. But at these two ends, it's very useful, because these two ends, we happen to know what the Fermi quasi-Fermi level is. Has to be equal to that, right? Just from this argument, they're communicating with that. And at the drain end, no matter what, we're going to go back to that, because it's communicated very closely with that. That we do know. In the middle, we don't know what the quasi-Fermi level is, so we don't think about it. All right? Okay. Yes.
I thought always that either the drain or the source, it doesn't really matter. One of those was always tied directly to the body. And
actually, that statement is not true. It may be easier to think that one of them is tied to bodies such as the source. But in a real circuit, many transistors, not just a few, many transistors have neither the body nor the drain tied to the, neither the source nor the drain tied to the body. And so just accept that, all right? And later we can even see some example how this is the case. But it should not bother us. We can see it. We can treat the source the same way as the drain, so we don't have to force one of them to be tied to the body. Actually, it does not introduce additional complexity, right? But in real circuit operation, often neither the source nor the drain is tied to the body. Okay. So any question? How mathematically we managed to get a relationship between ID and a VG and a VS and a VD and a VB. It's that. The equation is here. It involves phi SL and phi S0, and phi SL and phi S0 are given by two equations like that. All right? Now these are still not analytical equations. They require iteration in order to find the ID as a function of VG, VB, VS, and VD. But at least we have a way to do it. All right? Question?
Yeah, for equation 4.49 in slide
4.49.
Yeah.
4.49. Okay, here, on slide 6-3.
Yeah, for the equation of the inversion layer charge and phi s, where does that plus minus sign come from?
Okay. You know, every time you have a square root sign, you always have to think about this a little bit, right? And I don't even know immediately know how to answer this question right away.
Because of the
Pardon me?
substrate? Is that because of the type of the substrate?
Absolutely. You know, as you can see, this sign comes from this sign, right? So in order to figure out a sign, we have to come back to here and ask, you know, we know this is Q depletion. If the Q depletion is a, you know, ionized donor, should have one sign. Ionized acceptor has to be a sign. Another sign. Okay? All right? Okay. So the math is complicated, but somehow we managed to have this expression, and that's called a chart sheet model of the transistor IV. And if we plot that, you indeed will get one smooth curve Suppose you plot log ID versus VG, you get one smooth curve, right? You can also plot this for several VD, you see? And you can also do this for several VB, by the way, which I did not indicate. It actually tells IDs for any VG, any VD, VS, and VB, all right? Now, if you plot in the more familiar ID versus VD plot, same thing. We'll give you the set of curves, and in fact, we'll automatically give you curves for VD larger than VD set. Just give you this set of curves. Okay. All right. Any questions about the chart sheet model? Yes.
Going back to what I asked before, can you
Yes.
explain why having one, two, three, four? It's a four-terminal device. Why not having the source? How that affects its functioning in a circuit? Why you would want to have something with neither the source nor the drain tied to the
Sure.
to the body?
It's very simple. I just answered that.
How does that work differently than?
It's for necessity. Think about a NAND gate. As you know, NAND gate will be made of several P-type well, I will not draw the connection here. It's a bit complicated. Just look at the pull-down leg. You're going to have several N-type transistors in series, for example. Is that right? Each of these is connected to an input of this NAND gate. Is that right? Okay, this is called a NAND gate. This is one circuit, all right? So in this circuit, we have three sources. They are at a different location, so there's no way for them to all be tied together, to be all shorted all the time. And yet only have one body, because they're all made in the same wells, in one body. So just for this reason, source cannot always be tied to the body. Not that we prefer it for some reason, it's just we cannot. Right? It's necessity. Okay? All right. All right. So it's a model, but it's very complicated. And, this model has been known for several decades, but it has never found a lot of use. Very occasionally, a company may use that in a SPICE model. The last several years, however, I'll say maybe only 2 or 3 years, there seems to be a revival of interest in using this chart sheet model for compact modeling, for SPICE modeling, right? And that's one interesting thing about this chart sheet model. I really cannot think of applications where you use it by hand calculation in circuit design, just because, as I said, it doesn't seem to tell us a lot about physics. At least I haven't been able to figure out how to use this, other than when you use a computer, seeing SPICE model. It's certainly an option. All right? Okay, yes?
So, do these equations predict saturation?
It does predict saturation. And actually, I don't know the answer to that. Let me, I have to think a little bit more about this, and maybe Jane can help me answer this in a moment. Certainly, it will predict all these points up to where it's going to saturate. Now, if we just give it arbitrary large VD, will it predict a current that's equal to the current at A? It probably does. I wonder if Jane knows this answer. I think it does not? I see. What would it do? If it saturates at VD equal to 2 volts, and I put VD equal to 4 volts, or VDB equal to 4 volts, what will happen?
Yeah, when the device is biased at saturation current, saturation region, then the chart sheet model at the drain end will not fail.
Is that right?
Yeah.
All right.
So in this case, it's just available for the linear region.
I see. All right. So I take your word for it. Although, mathematically, if you look at this, it does seem that eventually, I don't know. I guess I just don't know how to, I take Jane's word for it. So this model is also only good up to VD set. Beyond VD set, you still have to make some physical argument and hold it at a constant. Is that right? All right. Okay, so there answers the question. That makes it actually somewhat less attractive then. Huh? You have to know when to stop using this equation, when to start holding the constant. Huh. All right. Okay. Yes?
So does the first current, the ID versus VG one, does it mean that subthreshold current is independent of VD?
Independent of what?
Of VD, the drain voltage?
The source, you mean the phi S? Or I'll say it again, or subthreshold current. Yeah. According to this model, yes, at least when VD is larger than several kT, you can show it's independent VD. Now, you may have remembered that for some reason this curve does shift a little bit with VD. Now, that has to do with something that's not captured by this model. It has to do with things like drain-induced barrier lowering. It's a subject of next chapter we'll talk about, all right? Usually having to do with short channel. So at least for long channel, subthreshold current is basically independent of VD, as long as VD is larger than, let's say, 20, 30 millivolts. Okay? Okay, other questions? All right. The textbook kind of start from here, do some things kind of unusual, but I thought it's also kind of interesting. It start with this very complex, sort of comprehensive IV characteristics, and then start to make some modifications or approximations, simplify the equation, and see how it then reduces to more familiar forms. And so let's just go through that. To simplify model, we can do several things. One thing, you can ignore diffusion. And by the way, since this equation does tell us which terms having to do with equation, diffusion, which term having to do with drift, one can quickly identify. This part is mostly come from the subthreshold current comes from the diffusion component. All right, and the diffusion component is negligible in this part. So the strong inversion region is all due to the drift component. All right? Okay. So we can ignore diffusion currents, one way we can do, and then maybe we can also ignore something that we can identify as the Q depletion, the bulk charge, and or we can limit ourselves only to the subthreshold regime. And by making assumptions, then this chart sheet model will yield some simpler special cases. So let's look at some special case. First special case textbook look is called strong inversion regime for section 4.5.4. What it does in this section is ignores the diffusion current and also assume that phi S is clamped at 2 phi B. All right? Now that's the usual assumption. Usual meaning, simple assumptions. Once the inversion, we reach the inversion, band bending is clamped at 2 phi B, does not continue to increase, right? Right? Our standard chart sheet model does not make the assumption, by the way. It assumes that phi S can continue to increase with increasing VG beyond VT, although phi S does not increase much, but it does increase, all right? So here we can make approximation that phi S is clamped at 2 phi B. Of course, in certain terms, this 2 phi B must still be increased by VSB or VDB, as we talk about today, right? Okay. So in that case, you can show that phi S0 becomes very simple, just 2 phi B plus VSB. 2 phi B because once the immersion happens, supposed to be pinged just at 2 phi B. But today we know in the presence of a body bias, the band bending actually is not 2 phi B, but 2 phi B plus VSB. All right? Okay. So just by doing that, and also VSL is equal to 2 phi B plus VDB, we no longer need to do any iteration to find out phi SL and phi S0 for any given VG and VD and VS anymore, right? Because as long as VG is larger than VT, phi S0, for example, is just equal to 2 phi B plus VSB. Is that right? No more to do any iteration. Is that right? Yeah? So if we now substitute these two into that full expression for IDS, right? Yes? And keeping only the drift term, this is what we get. Keeping only the drift term, this is what we get. Okay? Or maybe I'll give you just the, let's take a, you don't have to flip your notes to the earlier slide 6.4. Just we can see, you see, so these, for example, square root terms is not there, and instead we just have the linear term, square term, and 3/2 term, and each of these is only as simple as what? As 2 phi b plus VSB, example, right? Or minus VSB, and you will see. And we have that, right? So the 2 phi b is here, and I guess VSB, we, sorry, already rearranged terms somewhat, so now it's in the VDS, and rather than VDB, VSB now. So after rearranging some terms, we end up with that, but we still have the 3/2 power terms. Okay, we no longer have the square root term because we ignore those. They are in the diffusion terms. See that? Okay. So this came from simplification of that chart sheet model, and yet you may find that familiar. If you don't, that's all right, but I believe many of you in your first course of MOS theory, depending on which textbook you use, may have seen this curve. This is often derived in the first course of MOS theory. What's called is including the bulk charge effect, right? Including the bulk charge effect. If you include the bulk charge effect, this is what you will get, all right? Now, as I said the last time in the review of the MOS theory, I don't want to emphasize that because this is only good for uniform doping, and it's really not very good model, and we have a simpler model using that M, use a fixed depletion region thickness to understand the bulk charge effect or the backgate effect. We don't need the 3/2 power, right? But if you have seen this before, so here you see we can get to it. All right? And in order to get to this, you may remember what you did is you start this IV equation derivation using this equation. You said Qi is equal to Cox Vg minus VFB minus 2 phi b minus gamma square root of 2 phi b plus V in the channel, the potential in the channel minus the channel potential. All right? If you use this to begin with, you end up with equation like that. We can also make an approximation. That is, the Vt does not change throughout the channel, and in other words, Qit is simply equal to Cox times Vg minus Vt minus V. I guess last time we called this Vc, right? The channel voltage, VRVC, means the same thing. And if we start with that approximation, then we get an even simpler model. And this is the model that I ask you to memorize, and here I put it in the box again. We should memorize that, okay? You can obtain this simpler model from this equation 4.58. I guess it's a little complicated, so I will not do that with you, just by making the assumption that this term is negligible, okay? If you can make the assumption this term is negligible, gamma times, let's just put it away. All this is negligible, all right? It's not zero, but small enough so that you can use Taylor expansion to linearize these terms, all right? Linearize these two terms. If you make that assumption, which by the way means gamma is very small, or usually says when doping concentration is light, right? If you can make those kind of assumptions, you will end up with this equation, okay? And that's often said when the bulk charge effect, when the backgate effect is negligible. Although I did endorse this equation and said that it's very useful, and I want you to memorize this equation. If you memorize only one IV equation, this is the one. I did not quite stop there. I did say it is possible to remember a variation of it, which is very simple, and let me just remind you what that is, and that is this equation, right? This equation. All you do is you add a m here. Last time I introduced the m to replace 1 plus alpha. Today I just use alpha. Either way, use m was even easier, right? Just add an m to that 1/2 term. You get a much better model, and you would not have ignored the bulk charge effect. You would have included that effect, or you can call that backgate effect, and I think it's even a superior model, not only in terms of simplicity, but in fact in terms of accuracy compared to that 3/2 power term, because the 3/2 power term assumes a uniform doping, right? This constant m assumes a retrograde case, doping case. All right? All right. And the effect of that m is also shows up in VD set, right? Vg minus Vt over m. Also shows up in ID set, right? We have to divide ID set by m. Okay? All right, any questions about what we talk about today?
A question?
Yes?
What is the relationship between the bulk charge effect and early effect?
Bulk charge effect and?
Early effect.
Early effect, all right. Good, let's clarify that. All right. The two things are dealing with quite a different behavior. I'll first talk about early effect, then I'll say a little bit more about this bulk charge effect. You ask about early effect. Early effect describes the phenomena that some of you may know as the channel length modulation effect. Channel length modulation effect. The best way to explain this to describe this effect in a figure is really this curve, the ID versus VD plot. If we measure a transistor current, you will find it never truly saturates, always continues to increase with increasing VD even beyond VD set. That fact that ID set is not truly a constant, but rather it's a quantity that increases with increasing VD, that effect is called early effect. All right? That's called early effect. Now, it's widely, I suppose, taught that early effect is synonymous with channel length modulation, that this is caused by channel length modulation. Later in this course, we're going to show you that that's not necessarily true. In fact, the most dominant early effect that we see that really limits the operation of analog circuit is not result of channel length modulation. There are other physical phenomena that's responsible for early effect. So early effect itself is very, well, I suppose depending on how you define it. All right, I want this way. Early effect, this name itself, initially came from bipolar transistor, as you know. And there the mechanism, of course, is significantly different from the MOS transistor mechanism, in some ways different. So when Dr. Early first introduced this early effect concept, he correctly presented the physical phenomena or explained the physical mechanism for the bipolar transistor's early effect. He did not claim credit to explain this non-saturation for the MOS transistor IV. And later, when the transistor designers, I think it's really the transistor designer as opposed to the device physicist, started using this term to describe this phenomena, I think there was probably, one could assume there's no implied mechanism when this name was chosen. That is, this name just refers to the behavior in the IV plot, does not refer to any particular mechanism that causes this behavior. probably other people made a connection between early effect and this particular mechanism. And this particular mechanism, we have also seen in the review. It has to do with the fact that when VD is larger than VD set, there will be a finite region in the channel that will be consumed to dissipate the voltage VD minus VD set. As a result, the remainder of the channel, which determines the transistor current, becomes shorter. So this channel length shortening, channel length modulation is the mechanism that generally or often is used to describe the early effect. But later we'll see some other reasons why the current may not be constant. All right? Now, this is called early effect. Now, if that's clear, let's go back to this other name that you asked me to separate from the early effect. That's called bulk charge effect. Bulk charge effect describes some reason why the inversion charge is actually less than just Cox times Vg minus Vt minus V channel. It's actually less than that. Okay? And it turns out the answer is this quantity just give us all the charge in the body. You know, with the background of chapter 3, the first few weeks of lecture, I think you should be able to see that this really gives us the all the charge in the substrate, including at least the change of the charge in the substrate, including the change in the inversion charge, as well any additional change of charge in the depletion region. Okay, I will not get too much into that. I don't think it's necessary. Let's just say that any charge beyond any charge beyond Q, any charge in depletion region beyond Q NA W D max, any inversion layer charge beyond this component will have to be subtracted from the right-hand side in order to give us Q inversion. When we don't subtract anything from the right-hand side, we're assuming that the band bending does not increase between source and drain, right? In reality, we know that it will increase because band bending will increase beyond 25 V by this term, right? By this term. Whether this is VSB or VSD, sorry, whether this is VSB or VDB or anything in between. This quantity will determine the depletion region width. Right? We talk about here today that this actual band bending goes beyond 25B. It's for this reason that we cannot just use the fixed VT. All right. So phenomenon is pretty complicated, and by doing that, we are going to end up with an IV curve that's somewhat lower than without considering it. This effect is called bulk charge effect. Mathematically, it can be represented in the IV curve by adding some terms involving square root of VSB and so on and so forth to the 3/2 power, right? So those are the things associated with bulk charge effect. Now, what I want to add to this discussion is something that I introduced last time, which is not commonly introduced in this discussion. Is I actually think bulk charge effect should not be taught or need not to be taught separate from something called body effect. Right? Body effect simply says VT is a function of body bias, and specifically, I suggest it's linearly proportional to the body bias, right? And we can understand this by considering the fact that when we look at the Q inversion charge, it really should not be just Cox times Vg minus let's say V channel minus a constant Vt, but rather this Vt should really be our Vt0 plus the difference between the channel and the body. Maybe I should not call it source anymore. In the case of the transistor, when the channel potential is not equal to the source potential, the Vt should be equal to Vt0 plus alpha times Vcb. Can you see that? All right. So if we do this, immediately we see this is Vg minus Vt minus m times Vc. This m has to be increased. So this will then lead to the phenomena we wanted before. Firstly, we were looking for before. Firstly, we'll predict a current that's smaller. For example, the saturation current will be smaller by a factor m. Right? And mathematically, the result is quite simple. We show that ID set is reduced from the first order equation by m, right? Let's remind ourselves what are the quantities here. It's proportional to W, proportional to mu, C divided by 2L, right? There's a square term. So m would appear this way. So therefore, I think it's very good to remember there's a very strong link. And what this is describing is what classically is called the bulk charge effect. And yet I'm linking this to the body effect, which is that name is often associated with the threshold voltage. But I'm suggesting you to think that these two are one and the same effect. It all has to do with the fact that we have a back gate. Because we have a back gate, when the channel potential rises, there will be some decrease of the channel charge as a result of decrease of the voltage across the top capacitor between the channel and top gate. There's also a decrease of the channel charge because of the increase of let's say, of the voltage between the inversion layer and the bottom capacitor electrode, which is the body. So it's for this reason that we have a change in Vt, which also reflects in a reduction in ID, which is commonly called the bulk charge effect. All right? So if you start calling both the body effect, I think it's a very good way of thinking about it. Right? Okay, so other questions? I gave that a long answer because I think it is interesting and deserves that time. Also because I'm coming down to the last page of the notes for this lecture. There's really not much to say. So we can probably end the lecture a few minutes early. And so the next section in the textbook is called 4.5.6. It talks about SPICE model. And I thought the only thing we can talk about SPICE model at this point in the textbook, in the lecture, is really just point out that different levels of SPICE models treat the bulk charge effect differently. And this is one significant difference among this models. But of course, once you get into the details, there are a lot of other differences in the model. So before I tell you the difference in the way they treat the bulk charge effect, let me just say that I will devote one lecture later on in this course to a SPICE model, specifically talking about the BSEM model, because that is the most popular model today. It's an industry standard model, and that actually incorporates a lot of the physics that we'll be talking about in this course, not just having to do with IV, also having to do with short channel effect and maybe some other things that you don't anticipate. So after we have talked about those, I'll then give one lecture on the Beeson model to see how all these things can be used in the SPICE simulation model, in addition to be used as guidance for designing better transistors or understanding how transistors work or why these sometimes don't work. All right. So today, even though the textbook brings us to SPICE model section, there's really not much that we can say. I think that's interesting. So you'll read that section. Instead here, I just point out, if you ever had a chance of using the level 1 model in SPICE, it uses what we call the basic equation. That is, does not consider the bulk charge effect. So it will give us this equation. It will give us equation current is equal to L times C mu divided by W VGS minus VT minus 1/2 of VD times VD. All right? So that's called level 1. Now if you look at level 2 model, it considered the bulk charge model, includes this. And by the way, this is chronological order, right? That's the way the model were introduced chronologically, right? So when you look at this, you can also get a little sense of how the device physics has changed over the years, right? Start with, this was considered fine, good enough. Later, for better accuracy, it's felt this is a better model. And later, it's actually felt this doesn't give us a better necessarily give us a very accurate model, and also numerically it's just a little bit more complicated. Empirically, this seems to give us just as good fit, if sometimes not better, and certainly even simpler, right? So this is the model I think we should be teaching to our students, not that one, but that's still the one that's taught in all the textbooks. But my book will teach this, of course. So this is the level 3 uses already used this model. It's actually simpler. And Beeson 1 and 2 also continue to use this model, but Beeson 3 actually includes, I think, a more sophisticated model. That's the one that I will talk to you in some detail later on, after we have a look at other short channel phenomena. Then we'll talk about Beeson 3 model. Okay, any question in general about SPICE models? All right, anything, any question about the chart sheet IV model that we discussed today? Okay, so I'll see you next Tuesday.
Can I ask you?
Sure.